Alright, so in this video we're going to be treating an experiment on electricity, and the experiment is experiment E1, and the title is voltage and current in a circuit. Voltage and current in a circuit. So basically we have the experiment has been carried out and we have the results from this experiment. Here we have the voltmeter readings, the ammeter readings, and then the potential difference divided by the current. All right, the voltmeter readings and the ammeter readings were gotten from the voltmeter and ammeter respectively. Here we have V1, V2, I1, I2. And then our values of R1 and R2. R1 basically is the resistance. So it's gotten by dividing the potential difference of V1 as V1 by I1. That's how we get R1. R1 is simply V1 divided by I1. Then R2 is simply V2 divided by I2. Right, so basically that is what we have here for our readings. Now the questions, they said use the same axis to plot two graphs of V1 against I1 and the other of V2 against I2. So we're going to be plotting graphs here, and this is a special graph in the sense that we're plotting two graphs on one graph sheet. So first we have V1 against I1, and then we also have V2 against I2. Now to our graph sheet or to our graph paper, the first thing you need to know here in every graph is that the graph must have a title and it must have a scale. This is a question that has to do with plotting graphs of V against I. So our title will be a graph of V, all right? That's potential difference on the vertical against I being current on the horizontal. All right, V has the unit to be volts, we put it in brackets. Current has the unit to be ampere, we put it in brackets A. Now the scale. The scale for V axis we have 1 cm represents 0.2 volts, and then for I axis we have 2 cm represents 0.3 amps. I'm going to show you a simple method of getting your scale for any graph. And how do you go about such? It's very easy. All you need to do is calculate the interval for that graph. Interval. Now the interval is simply the highest value, all right, from your table of values, the highest minus the least. The highest minus the least divided by the number of thick grid lines. Thick grid lines on that axis. So let's say, for instance, we want to get the scale for our vertical, because the scale for your vertical must not be exactly the same scale for the horizontal. It all depends on the values. So to get the scale for the vertical, we go to our table of values for the vertical, which is V. Now it's very important to understand here that your V is not just V1, but V1 and V2 combined. So when taking your scale, you must consider the two of them. All right. So look at V1 and V2 combined. What's the highest value for V1 and V2 combined, and what's the least value? Now, if you observe very well, the highest value we have here for V1 and V2 combined is 1.5, and then the least is from 0.2. Okay. So our interval here will be 1.5 minus 0.2 divided by the number of thick grid lines. All right, so we'll count our grid lines up on the vertical. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. All right, the thick grid lines, not the small ones inside, but the big ones. So we have 1.5 minus 0.2 divided by 10. That will give us our lower interval. Right, so that gives us 0.13. All right, now this is your lower interval. To get the upper interval, you multiply this by 2. So we have 0.13 times 2. That gives us 0.26. All right, so our scale now will be any number, all right, between 0.13 to 0.26. Okay, any number between this and this. So I decided to go with 0.2. Now this is the logic here. You need to go with a number that will be very easy for you to use, a number that is easily divisible. All right, so whenever you want to get the smaller components, you're not going to be having a recurring decimal all the time. right? So I decided to go with 0.2, which is in between 0.13 to 0.26. So we're going to check now. Check now if 0.2 is going to cover, 0.2 interval is going to cover all our readings. So we have 0.2, 0.4, 0.6 up to 1.8. The highest value here is 1.5. So you can see that 0.2 can actually cover everything. All right, and then the least value is actually 0.2. So that's what we have. So that's how we got the scale here to be 1 cm represents 0.2 volts. 1 cm, each box here, each big box that is bounded by the thick grid lines is 1 cm. So we say 1 cm represents 0.2 volts. Okay, 0.2 volts. And then for the y-axis, the same method we use in getting our scale for the v-axis, we're going to apply it again in the y-axis. So we'll go to the y-axis, we'll look at our table of values. We have I1 and I2, all right, combined. What's the highest value for the two of them together? You can see that your highest value is 1.6 and then your least value is 0.1. All right, and then we'll also count the number of grid lines. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. All right, so simply say 1.6, okay, being the highest value, minus the least value, which is 0.1, divided by 15. 1.6 minus 0.1, and that will give you 1.5. You divide it by 15. We have 0.1. Then we multiply by 2, we get 0.2. All right, so we choose any number from 0.1, okay, to 0.2. Now we cannot go with 0.1. The reason is if we try 0.1, it's not going to cover all our readings. Remember, your highest value here is 1.6. Now watch, we have 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1, 1.1, 1.2, 1.3, 1.4, 1.5. So you see it's not covering everything. All right. Now, if we now try 0.2, 0.2 will be too small. 0.2, 0.4, 0.6, 0.8, 1, 1.2, 1.4, 1.6 is a very small graph. The essence of choosing a scale is so that your graph will not be too small. All right, your graph must cover at least 2/3 of your graph paper. So that's what we're trying to achieve. So since 0.1 and 0.2, which are very good numbers, are not working here, we go for a number between it, which is from 0.1 to 0.2. A perfect number we can go with is 0.15. All right, now this 0.15, the next one is going to be 0.3. If we add 0.15 to 0.3, we have 0.45. All right, if you have 0.15 to 0.45, this is 0.6. If you add 0.15 to 0.6, this will give you 0.75. You have 0.15 to this, you have 0.9. But to make it easier, rather than having two decimal places everywhere, we just decided to say, okay, let's go with two boxes, 0.3, two boxes, 0.3 interval. All right, so if this is 0.15, one box 0.15, two boxes will be 0.3. So we have 0.3 interval. It was still from this calculation. 0.3 interval, two box, the next one will be 0.6, the next one will be 0.9, 1.2, 1.5, 1.8, just like that. So that is our scale for the horizontal. All right, now the next step, so that's how we arrive at scale for the horizontal. You can see we have two boxes being 2 cm to 0.3 amps. So that's just it. So now the next step will be to plot our points. Now to plot our points, you can see here I've already plotted the points, but then there's one thing you need to know here. To plot your points, you need to know the value of each thick and each thin line on your horizontal and on your vertical. So now for our v-axis, that's horizontal, all right, each thick line, as you can see here, is 0.2, all right, it's increasing by 0.2 interval, so we have 0.2, all right. Now for the thin lines, which is very important here, each thin line, now to get it here, you discover that you have 4 small boxes inside every big box. Let's count it. Towards the vertical here, we have 1, 2, 3, and 4. So because of that, we divide by 4, all right, to get the value of each thin line inside the big box vertically. On your normal graph paper, you may have 5 small boxes. So in that case, you divide by 5 and not 4. All right. In your own case, you divide by 5 because you have 5 small boxes. You can count it. 1, 2, 3, 4. Your own may give you 5 vertically, and then also 5 horizontally. All right. So here we have 4 vertically and horizontally. So we divide by 4. So we're going to have 0.2 divided by 4. And then that will give you 0.05. So if that's the case, if you observe, if you want to confirm, this is 0.4, 0.45, by the time you add 0.05 to it, and then the next will be 0.5, okay, the next will be 0.55, if you add 0.05 again, you have 0.6, so that's it. So for the v-axis, this is what we have. Now for the y-axis, it's good you just write all these things out so that it will be very easy when you want to get your points. For the y-axis, you discover that each thick line, all right, increases by 0.15. Now if 2 boxes is 0.3, just one will be 0.15. Remember, we calculated this already to be 0.15. All right, from here to here is 2 boxes, we have 0.3. One of them will be 0.3 divided by the 2 boxes, which is 0.15. All right, so this is 0.15. This is 0.15. We have 0.3. The next one will be 0.45. Okay, now for the thin lines, or the small lines inside the big box, if this is 0.15, to get the value of each small one here, we divide 0.15 by 4, all right, just like we did for the vertical. This is now horizontal, so we have 0.15 divided by 4, and that will give us 0.0375. 0.0375. All right, now we can plot our points. Here we have 0.2 for v1. All right, please, we have to plot v1 and i1 first, okay, and then we get our line of best fit, calculate our slope before we go to that of v2 and i2. All right, so that we don't have all the points together, then we just mix them up and it's going to be really complicated. So we'll get v1 and i1. Now when v1 is 0.2, i1 is 0.1. v1 being 0.2, i1 is what? 0.1. So now we'll go to our v-axis, we get 0.2. For our y-axis, we need to get 0.1. Now how do we get 0.1? This is 0.3. Now remember, this is 0.15. All right, to get the value of the next one here, which is 0.15, remember each small line on the horizontal, all right, is 0.0375. So it's 0.15 minus 0.0375. Okay, so we have 0.15 minus 0.0375, and that will give us 0.11. Okay, which is the next one. And 0.11 is actually very close to 0.1. It's actually very close to 0.1. So we can just take it. It's approximately 0.1. So we'll take it here, 0.1 and 0.2. Mark it down. And then the next one here is 0.3 and 0.1. 0.3 and 0.1. Now if this is 0.2, this is 0.4. 0.3 has to be between 0.2 and 0.4. So now we start from 0.4. We subtract the interval here. Remember, each thin line increased by 0.05. So we have 0.05 here. Which is 0.4 minus 0.05 will give us the next one, which is 0.35. Subtract another 0.05. you have 0.3. All right, so 0.3 is around here. All right, and then don't forget we already got the position of 0.1 on the horizontal to be around there, so that's how we mark this down. All right, now the next one is 0.6. You can see 0.6 and then 0.25. So we have 0.6 on our vertical. Now 0.25, if you observe this 0.3, all right, to get 0.25 we subtract 0.0375, which is the value of each thin line on the horizontal. All right, so 0.3 minus 0.0375, and that's 0.2625. That's the value we have here. If you subtract another 0.0375, you have 0.225, which is actually very far from 0.2625. We have 0.225 and 0.2625. All right, so between these two numbers, which is closer to 0.25? Discover that this is approximately 0.23 and this is just 0.26. All right, so 0.26 is actually closer, so that's why we'll go with this one. I'll just go with a point in between the two of them. I just decided to go with 0.2625, which is the next one here. All right, then I mark down this point. So that's just how we keep on marking everything. All right, you can check, pause this video and then check the other values, see that they're actually on point. Now if you observe the last one here, we have 1.4 and 0.6. 1.4 the horizontal, 0.6. So after plotting your points, the next thing now will be to get your line of best fit. Now in getting your line of best fit, please always ensure that your line of best fit is balanced. All right, it doesn't necessarily have to pass through any points or pass through all the points. Your line of best fit should just be in a position whereby it is at equal distances from all the points, almost average distances from all the points. All right, it's not too far from any point. All together, the points that do not enter your line of best fit should appear on both sides, not just in a case whereby you have all the points appearing on just one side, that's just above the line or below the line. That's wrong. All right, so now we need to get our line of best fit. Now this is what your line of best fit for this graph will look like. All right, you can see what it looks like here. Okay, you can see we have a point here and we have a point here. All right, the point that did not enter on both sides and they just centralized. We're not come to draw this thing in such a way that we just took only some points. No, it is balanced. All right, then after that you need to get your slope. To get your slope, you choose any 2 points on this line. The points should just be points that are easy to reach. You can easily get their values. So here I went with these 2 points here. Please, the points should not be too close to each other. All right, neither should they be too far from each other. So I went with this and this. If the points are too close, it's going to be a very small triangle. You're going to get a very small triangle, and that's bad. That's wrong. That's a bad graph. All right, so here I went with this and this. From the point up, I draw a straight vertical line. From the point down, I draw a straight horizontal line. Connect the two of them, and then I have a right angle triangle. All right, then we trace it to our vertical and then to our horizontal. So for the slope has a formula. Mathematically, slope is equal to change in vertical. Our vertical is potential difference here, V axis. So change in V all over. Our horizontal here is I, which is current, over change in I. All right, slope is change in V over change in I. All right, so now we go to our V axis. We want to get change in V. Simply the final V minus the initial V. So this is what we have here, and this is what we have here. This is 1.6. The next value here, you minus 0.05. So that will give us 1.55. So you have 1.55 minus, and then here we have 0.2. all over. Now here, if you trace it down, here is 0.6. If you add 0.15, don't forget each one here is 0 increases by 0.15. So 0.6, the next one here plus 0.15 will give us 0.75. So you have 0.75 minus the value we have here. If you trace it down, don't forget each small line on the horizontal is 0.0375. We calculated it already. So we have 0.0375. Okay, and that will give us our slope now to be 1.55 minus 0.2 divided by 0.75 minus 0.0375, and that is actually 1.89. Our slope is 1.89. Now most times your slope will carry a unit except the quantities that are dividing have the same unit. In this case we have potential volts and we have ampere. All right, so the units are not the same, so the slope in this case has a unit. So what's the unit of the slope? If you observe, this potential difference dividing current. All right, potential difference divided by current is resistance, and what's the unit for resistance? Ohms. So it simply means our slope will bear the unit ohms, 1.89 ohms. All right, so now if you see 1b part, question 1b, they say measure and record the slopes of two graphs k1 and k2. So this graph here, the first one is k1. So please have it at the back of your mind that slope of k1 is 1.89 ohms. All right, 1.89 ohms. Now it's time to get that of k2. Now after plotting k1 as a first graph and getting your line of base fit and calculating your slope, then you can now go to the second graph, that's v2 and i2. Okay, it's best to do it this way, then you go to the next one so you don't mix the points. All right, so this is v2 and i2. I've already plotted the points using the same scale. All right, remember the scale we chose was for both v1, v2, i1 and i2. So using the same scale, we plot v1, v2 against i2. All right, if you observe here, see the first point, 1.5 and 0.1. Okay, so 1.5 and 0.8. Okay, so we'll go to our v-axis. This is 1.6. Where are we going to have 1.5? This is 1.6 minus 0.05, 1.55 minus 0.05. We have 1.5. All right, so this is 1.5 around here. Now 0.1, we have 1.5 and 0.8 rather. 0.8, where is it supposed to be found? 0.8 should be between 0.6 and 0.9. All right, so if this 0.9, to get 0.8, remember each thin line increased by 0.0375. So say 0.9 minus 0.0375. And that will give us 0.8625. Remember, what we want to get is 0.8. Okay, so subtract again 0.0375. And this is 0.825, which is actually very close to 0.8. So from here, subtract the first one, subtract again, then you trace it up to meet your 1.5, and you mark the point, which is this. Okay, the next point here we have was 1.4. all right, which is what we have here, 1.4 and 1.4 and 0.8 again. Okay, so trace it down again. I will still mark the points. That's what we have here. And then after that, the next one was 1.3, which we calculated to be around here, 1.3 and 0.7. all right, 0.7. This is 0.75. 0.6, you add 0.15 to 8, 0.75. So to get 0.7, we say 0.75 minus the value of each, the interval for each small thin line is 0.0375. So we have 0.7 minus 0.0375. Sorry, 0.75 rather, 0.75 minus 0.0375. That's 0.7125, which is actually very close to 0.7. So choose somewhere around here. All right, 0.7. and then 1.3 can be gotten. This 1.4, 1.35. By the time we minus 0.05, then we have 1.3. We'll mark it down. The same thing applies to all the other 2 points, or to all the other points. All right, all the other points. For the next one here, you can see we have 0.9, all right, and 0.9. So 0.9 on the horizontal, 0.9 on the vertical. This is 1. You subtract 0.05, all right, you have 0.95. Subtract another 0.05, you have 0.9. So you mark it down. The same thing there. Now you discover that for the second plot, that's V2 and I2, is actually very scattered. So it don't make sense to now come here and draw your line of best fit. We are done with plotting our points. So the next step here is to draw the line of best fit for V2 and I2. So it will be wrong to draw your line of best fit like this, because you see that all the points that did not enter on one side, and the line is actually very far, all right, from all the points. So the best way is to just draw it in between everything, all right. So I can just draw it through these points here, so that the points that did not enter will be on both sides and the graph will be balanced. The line should not be too far from any point. It should just be around all the points combined. So this is what our line of best fit for V2 and I2 looks like. All right, and this will give us K2. All right, the line of best fit for V2 and I2. You can see it here. It just passes through one point and it is not far. All right, it is just around all the points combined. This one and this one are at almost equal distance from it. You have points appearing on both sides. So this is your line of best fit here. Okay, and then you use it to calculate your slope. Now to calculate the slope again, don't forget the slope for K1. Slope for K1, we already calculated it to be 1.89 ohms. All right, K1 is 1.89 ohms. Now K2 is what we want to calculate. Now again, we choose any 2 points on this line of best fit. It must not be a plotted point, but then the points should not be close to each other. All right, they should be in such a way that we are going to have a big right angle triangle, because from the point up we draw a straight line down, from the point down we draw a straight horizontal line towards the right, and then where they meet each other we stop and get a right angle triangle. Okay, so our slope again, slope is simply change in vertical, which is potential difference, V axis, change in V, all over change in horizontal, which is I. So we have delta I. All right, so now we say slope equals delta V. Check your change in vertical. This is 1.6, and then your change in horizontal, your final value on the vertical, if you trace it from here, 1.6, and then here you have 0.4. So we have 1.6 minus 0.4 all over, here we have this 1.5, or 0.15 is 1.65. Okay, so we have 1.65 minus, now if you observe here, this point here, this is 0.3, this is 0.45. So now the value here, which is 0.45 minus 0.0375. Remember, on the horizontal, each small line or thin line increases by 0.0375. So we have 0.45 minus 0.0375, and that is 0.4125. That's the value of this point here. Okay, so we have 0.4125. Okay, now by the time we divide, subtract, and then divide, we have 1.6 minus 0.4, all divided by 1.65 minus 0.4125. That will give us approximately 0.97. So we have 0.97. Again, our unit for slope will be ohms. All right, because we have potential difference divided by current, which is resistance. So slope 2, that's K2, will be equal to 0.97 ohms. Slope 1 is 1.89 ohms. Slope 2, K2 is 0.97 ohms. Now your answer may not be exactly what I have here, all right? It all depends on your readings. So work with your own readings. And then it also depends on the kind of graph paper you're using, all right? So work based on your graph paper. But then you just need to understand that your value of K1 must be greater than your value of K2. That's just the concept here, all right? The slope, K1 is the slope for series. K2 is the slope for parallel, all right? So the slope for series must be higher than the slope for parallel because K represents resistance. So resistance for series combined is higher than resistance for parallel combined. So that's it there. Whatever value you get, you can just work with it, right? Work with whatever value you get, but then you need to understand that Q1 should be higher than K2. All right, so we've answered question 1A and 1B. It said use the same axis to plot two graphs of V1 against I1 and the other of V2 against I2, which is what we have here. Measure and record the slopes of K1 and K2. This is what we have here. Now the next question, they say, what do the slopes represent? Now the slopes represent a resistance. That's your answer there. Now 2B, does your experiment agree with theory from the values of K1 and K2? All right, now we simply answer it this way. From the experiment, the resistance of series, yes, it actually agrees with the values of K1 and K2. All right. From the experiment, you see that resistance for series connection were always seen to be higher than resistance for parallel connection. You can go back to the table of values and confirm. All right, the resistance of series were always higher than that of their corresponding values for parallel. All right, so and also we have that this was also seen in the values of K1 and K2. Discover that K1 means slope for series, slope resistance. All right, the resistance for series, and K2 being resistance for parallel was higher than K1 was higher than K2. K1 being the resistance for series, K2 being resistance for parallel. K1 was higher than K2. Now we also have it said that the value of K1 was higher than that of K2, thus agreeing with the theory that says equivalent resistance for series connection of resistors is usually higher than equivalent resistance for parallel connection of resistors. So that's our answer for question 2B. Now for question 2C, they say draw the circuit for the parallel connection. This is what the circuit for the parallel connection looks like. The parallel connection, though I didn't show us the series connection is what came with the question, the practical itself. All right, this is the circuit for parallel connection. In the parallel connection, you have the rheostat resistor and the standard resistor being in parallel. But for the series connection, rheostat and standard resistors were in series. All right, for the series connection, we have the rheostat and the standard resistors to be in series. Now for the parallel connection, we have the rheostat and the standard resistor to be in parallel. Everything remains the same. We have our cell or battery down to the key or switch. We have the ammeter, and we have our resistors, and then we have our voltmeter. So this is the circuit for parallel connection. Please, in drawing your own, ensure your line is as neat and straight as possible. This is just a rough sketch. Now question 2D, they say, what can you say about the current and voltages for the series and parallel connections? Why are they different? Now for series, the same current flows through all components, all right? Whereas for the parallel, the voltage varies. Why? The voltage varies because they divide across components based on their resistance. And then for parallel, we have the voltage across each branch to be the same. The voltage across each branch to be the same, whereas the current is different because it divides depending on the resistance of each branch. Now, they say there, why are they different? Now, they are different because of how energy and charge distribute in different circuit configurations. Now, question 2E, it says, on what factors does the current in a conductor depend? Now, the current depends on the voltage applied across it, resistance of the conductor, nature of the material of the conductor, which is sometimes called the resistivity, the cross-sectional area, length of the conductor, and temperature of the conductor. Question 2F, they say, what would you expect if you increase or reduce the voltages in each experiment? Increasing voltage will increase current. This is Ohm's law. All right, current is directly proportional to the potential difference. So an increase in voltage will cause an increase in current, whereas decreasing voltage will reduce current. Now, this linear relationship holds as long as the resistance remains constant. That's for ohmic conductors, only applicable for ohmic conductors. Now, 2G, it says, what are the advantages or disadvantages of such increase or reduction? Advantages: increasing voltage can increase power output in devices, whereas lower voltage can reduce power consumption and overheating. Whereas the disadvantage, we have higher voltage may damage components or overheat wires. Too low voltage might not power devices effectively. So this is what we have for experiment E1. All right. So please do well to subscribe to this channel if you're yet to subscribe. And also don't forget to turn on the notification button so that whenever we post a new video, you would be notified. And also do well to share and like. All right, share to your friends and colleagues who this video might be of importance to, and don't forget to like and subscribe as well. See you in the next video.